Welcome back to the ICE and D1 series, and in this video we'll be having an in-depth look at switches. So let's just go over a quick recap of what we already know about switches. A switch is a layer 2 device, resides the layer 2 of the OSI model, and allows devices to connect to a local area network and communicate. So any device that connects to a switch, essentially a switch gives us a star topology. Now when devices on the same local area network want to communicate, they send their packet to the switch, and the switch will forward that packet out the correct ports. Now the switch itself is a third generation device. Devices that came before the switch were hubs and bridges. So with a hub was a layer 1 device, and it was a shared network segment in the devices that connected to this device were all part of the same collision domain, which meant that if two devices tried to send data at the same time, their data would collide. They would have to back off, and then they'd have to try to resend at a later time. And a hub was a very intelligent device, because when one device tried to send data, that data was delivered to every single device connected to the hub. Now with the bridge essentially split up our network into different collision domains. So with a bridge, each port represented a collision domain, which meant that this hub was in a separate collision domain, and this hub was in a separate collision domain as well. Now bridges were software based, which means that they processed everything software, which made them slow. The switch came along and was essentially a combination of both. With a switch, each port represents its own collision domain. Each port is its own network segment. So when you think of network segment, just think of a collision domain. So what that meant was that we could have multiple devices sending and receiving data and frames at the same time. Now with a switch also represented a single broadcast domain. Well, a broadcast message is a message sent by one device, and that message is delivered to all other devices on our local area network. So if device A was to send a broadcast message, device B, C, and D would also receive that broadcast message, and the switch would forward that broadcast message onto another switch uplink, who would forward it at all of its ports as well. So with a switch, each port represents its own network segment. So if I draw a quick diagram, so this is a hub, we have a switch over here, and we have a device over here. So in this case, you have some devices, would be one collision domain, one network segment, and this would be one collision domain and one network segment, and this would be a separate collision domain and network segment. So as you can see, with a hub, the whole device represents a collision domain, which means that only one device can send and receive at the same time. With a switch, each port represents its own collision domain. So in the Ethernet protocol, it defines that devices are able to communicate and share information by using their MAC address. All a MAC address is, it's a 48-bit number in hexadecimal format given to the device during its time of manufacture, and each MAC address is a globally unique address. And a switch is intelligent because it actually learns the MAC address of devices that connect to it. So the way this occurs is, let's say that two devices want to send and receive data. Okay, let's say that you have PCA and PCB. So PCA and PCB want to send and receive data. Okay, when PCA is building that frame to send to PCB, which contains all the data, it puts in its source MAC address and the destination MAC address. When the switch receives that frame, it looks at the source MAC address and notes the port that it received the frame on. It then notes the VLAN of that port. So what the switch actually does, as it receives traffic, it notes the traffic received on that port, it knows the source MAC address of the traffic received on that port, and then links that MAC address to that port. So it would know that to reach PCA, it can use the MAC address of so it knows that the device's MAC address of all ones lives off port 1, and that the MAC address of all twos lives off port 2. So a switch learns a MAC address by receiving frames. It looks at the source MAC address of those frames, and then maps that MAC address to the port it received the frame on. That's how a switch learns MAC addresses. So a switch will store the MAC addresses it learns about in content addressable memories. That's a special table in hardware. It stores the MAC addresses in binary, so in zeros and ones, And CAM is, you can think of CAM as being just like random access memory, like RAM, but it's much, much faster. And so the default aging timer for MAC addresses is 300 seconds. So what that means, that once a switch has learned of a MAC address, it will store it in its CAM table for, by default, of 5 minutes. If a switch doesn't receive data or any packets from a device with that MAC address on that port for 5 minutes, it's going to age out the timer, and what that means is going to remove that entry from its CAM table. That means that when it starts receiving packets again from that device, then it will add to its table. So as an example, let's say that PCA communicates with its PCB. Okay, PCA has a MAC address of all ones. The switch will store that MAC address in its CAM table. Okay, it will also note the port that the MAC address will learn and the VLAN. We will talk about VLANs in a later video, but just for now, just know that a switch stores all 3 pieces of information in its CAM table. Now, if the switch, which is this is very unlikely, if the switch doesn't receive any data at all from PCA, it will forget about that entry and remove it from its CAM table. The reason why I say it's very unlikely is because devices in an IP-based network, in an Ethernet network, are always sending broadcast messages. Broadcast messages are messages that are sent to all the devices on our network. Because they're always sending broadcast messages, it means that devices are always sending some sort of data to the switch, which means that the switch will always refresh its CAM table. So what happens, as soon as a switch receives data from PCA or from any device, it's going to refresh that aging timer. So in this case, let's say that it receives data from PCA. After about 10 to 15 seconds, the aging time has been decremented to 285. When it receives data from PCA again, it's going to set the aging timer back to 300 seconds and then wait another 300 seconds before it ages out that timer. So every time it receives traffic from a device, the aging timer for that entry is refreshed. And frames are forwarded based on the destination MAC address. So with a switch, when a switch receives a frame from a device, that's a PCA is communicating with PCB. When it looks to forward that data, it looks at the destination MAC address, and based on that MAC address, it will forward that data out the correct port. So in this case, when PCA wants to communicate with PCB, it's going to look at PCB's MAC address. So let's say PCB is the MAC address of all 2s. Look at PCB's MAC address and then decide based on that MAC address where it's going to forward that port, whether it's going to forward that frame out a port to another switch, or whether it's going to forward that frame to a particular device. It's based on the destination MAC address of on where the switch will forward a frame. And let's say that a switch doesn't actually have an entry in this CAM table for a MAC address. So in this case, let's go back to our example that we've been using in every slide. When PCA wants to communicate with PCB, imagine that the switch doesn't have PCB's MAC address in its CAM table. What does it do then? Well, the switch is smart enough to know that if it doesn't have PCB's MAC address in its MAC address table, it's smart enough to know that if PCA wants to communicate with PCB and PCA has got PCB's MAC address, it means that PCB must exist somewhere on this network. So all a switch does is broadcast that frame at every single port, hoping that PCB will receive it. PCB is going to receive it, and once PCB receives that frame, it's going to send data back to PCA, and then when the switch receives that data, it's going to learn of PCB's MAC address and the port associated with that MAC address, so it'll be able to put an entry with PCB in this CAM table. And that will list the MAC address, the port associated with the MAC address, and the VLAN. Now, when devices want to communicate, let's say when PCA wanted to communicate with its PCB, how does PCA know about PCB's MAC address? It's because our devices have what's called an ARP cache. An ARP cache just lists each device's IP address in the network, as well as the MAC address the device can use to reach that device. Now, how does a device learn of that mapping? How does it learn of the MAC address of a device? Because it uses what's called the Address Resolution Protocol, the ARP protocol. So devices communicate by using their IP addresses. As an example, when 2 devices in the same network or even in different networks want to communicate, they communicate by sending data to the to a certain device's IP address. So devices communicate using their IP address. So as an example, PCA and PCB want to communicate. When PCA sends data, not only does it list PCB's MAC address, but it also lists PCB's IP address. Remember, the latency protocols just define addressing and how to move data between devices in the same network. For PCA to determine whether PCB is in the same network, it has to know PCB's IP address, which is why we use IP addresses for communication. Now with ARP, the address resolution protocol says that when you know of a device's IP address, but you don't know of a device's MAC address, you can use the ARP protocol to find that out. So with ARP, essentially, PCA is going to send a broadcast message. A broadcast message is delivered to all hosts on the network, and this broadcast message says that if you have this IP address, so imagine that PCB has the IP address 1.1.1.2, and PCA has the IP address 1.1.1.1. The ARP message says, if you have the IP address 1.1.1.2 and you receive this message, please respond back to me with your MAC address. So it will forward that packet, that frame at every single port. When PCB receives it, it looks at the message and see, oh, okay, wait a minute, this frame was sent to me. This frame was meant for me because it's listing my IP address. So in my ARP cache, I'm going to put the IP address of PCA as well as the MAC address and store that in my ARP cache, because when PCA originally sent this message, it lists that information as well. Now PCB sends that message directly back to PCA because it's got PCA's MAC address and it knows PCA's IP address. So that message is sent directly back to PCA. In the source part of the message, it's going to list its IP address as well as its MAC address, in case it's MAC address of all twos. So now when PCA receives that message, it stores in its ARP cache the information listed in the message, so the IP address of PCB as well as the MAC address, and now it can send data directly to PCB without having to bother any other device on a network. And through this process, the switch will also learn the port that PCA resides on and the port that PCB resides on, and will put the information into its MAC address table. So we reached the end of this video, and before I wrap up, I just want to go through the whole process again from start to finish. So when two devices want to communicate, they will use their MAC addresses. And in this case, PCA wants to communicate with PCB. PCA realizes that PCB lives on the same network as itself because it compares the network part of its IP address to the network part of PCB's IP address. It realizes, okay, this guy lives on the same network as me, so now I have to communicate with him. But PCA doesn't know PCB's MAC address. So PCA is going to send an ARP request message to all the devices on the network. It's forwarded in this direction, saying that if you have this IP address, if you have the IP address 1.1.1.2, please respond back to me with your MAC address. PCB is going to receive it, and in this ARP cache, is going to store the information in the message. So it's going to store 1.1.1.1 and this MAC address in its ARP cache, so that it knows how to reach PCA. They're going to send it back a direct message to PCA. And in that message, it's going to list its IP address and its MAC address, so now PCA has all the information it needs in order to communicate with PCB. During this process of sending and receiving traffic, obviously the switches are the ones that are forwarding these frames between PCA and PCB. When the switch receives the frame from PCA, this broadcast message, it notes the port that frame was received on, as well as the source MAC address of that port, and creates the entry in its CAM table. And then forwards us onto this switch, and this switch does the same thing. It notes the frame that the port that the frame was received on, as well as the MAC address of the source MAC address of that frame. When PCB responds, the exact same thing happens. This switch is called the switch 2 and switch 1. Switch 2 notes the port the frame was received on, as well as the source MAC address of that frame, and switch 1 does the same thing. So now switch 1 knows it can reach PCB by trying to use port 2, and same thing as port 2. But switch 2 knows, in this case, let's say we have this device, if it receives traffic from this device here, switch 2 knows that it can reach both PCA and let's say PCC using port 1. So with the MAC address table, we don't just associate one MAC address with each port, we have the ability to associate multiple MAC addresses with a single port, and that depends on the number of source MAC addresses we receive on this port. So in this case, any new source MAC address that switch 2 received on this port, it's going to note down in the CAN table. So it's going to note down in the MAC address table that I can reach devices with MAC address 3.3.3.3 and devices with MAC address 1111 by using this single port. So normally, when we have an uplink to another switch, that port will have loads of MAC address table entries because we can reach multiple devices using that single port. So we've reached the end of this video, and we've looked at how switches work. We've looked at the fundamentals of switches in general. I hope this has been informative for you, and I'd like to thank you for viewing.